Hello everyone. In this video, we're going to take a look at an interesting optical phenomenon called a 22-degree halo. Now, I've never seen one of these myself, but supposedly if you look up at the moon on a very cold night, you'll sometimes be able to see one of these things that you see at the bottom left of this slide here, which is just this bright ring of light surrounding the moon. Okay, now the angular radius of that ring of light, in other words, the angular distance from the center of the moon up to the inner edge of the ring, is around 22 degrees, which is, of course, where the name 22-degree halo comes from. And note that we have to measure it in terms of angular size because it doesn't really have a physical extent in kilometers or anything like that. Okay, so what we're going to do in this video is explain the origin of this 22-degree halo in terms of refraction of light coming from the moon by ice crystals in the Earth's atmosphere. So I'm just going to delete this picture down here to make some room, and we'll start looking at the physics behind this. So you'll notice that I've drawn an equilateral triangle up at the top here. The reason for that is that ice crystals have a hexagonal symmetry, and we can understand to a pretty good approximation how a hexagonal crystal will refract light by understanding how an equilateral triangle will refract light. Okay, the reason why that works is we'll just imagine cutting off a small equilateral triangle from each corner of the big equilateral triangle, right? So I'm not going to do this particularly accurately, but something like this, right? And hopefully you'll be convinced that the shape that you'll be left behind with in the middle here is actually a nice regular hexagon. So to a pretty good approximation, we can understand how an ice crystal refracts light by just studying an equilateral triangle. Okay, so what we're going to do is think about the path of a light ray that is incident on one side of this prism, or one face of this prism because it's in 3D really, and think about how much it's kind of deflected from its incoming path. Right, so if we imagine a light ray coming in from this bottom edge, which I'm going to draw like that, okay? Now, I'm going to define a bunch of angles, and I'm going to say the incoming angle is going to be alpha. Okay, now what's going to happen is the ice crystal is more optically dense than the air surrounding it, and so that light ray is going to bend towards the normal, right? In other words, it's going to do something like that. Okay, so it's bent towards the normal. And if I define this angle of refraction here as beta, then you can see beta is smaller than alpha. Okay, so then another refraction is going to take place at this interface over here on this other face at the top, right? And so this time it's going, the light ray, it's coming like that. It's going from a more optically dense medium to a less optically dense medium, and so it's going to bend away from the normal this time. And in other words, it's going to do something like that. So if I define a couple more angles, that one there can be called a gamma, so the angle of incidence on the upper face, and then the angle of refraction coming out the other side of the prism, I'm going to call delta, like that. This time delta is bigger than gamma. Okay, now to understand, or to get an idea of the overall effect that the prism has had on the incoming light ray, we can calculate the overall angle of deflection, right? In other words, what I mean by that is, let me just draw, I'm going to extend the incoming ray like that. So this is not what the ray is actually doing, but just for geometrical purposes, I'm extending that ray, right? And we can define an angle all the way from the outgoing path to the incoming path. And let's call that theta. And that's going to be the overall angle of deflection, right? So if we kind of knew what theta was, we wouldn't have to understand the details of what's going on inside the prism. So what we're going to aim to do is calculate how this theta depends on the incoming angle. Okay, so in order to make the calculation of theta a bit simpler, we're going to split theta up into two parts, right? So we're going to split it up into the deflection caused by the first refraction, and then the deflection caused by the second refraction. So in other words, we have a little bit of deflection when the light ray first comes in and comes into the crystal, right down here, I'm going to call that theta 0, right? And then, if you imagine what happens up at the top here, well, we could extend this path of the light, all right? So if there were no refraction at the second interface, it would just continue along that line. And then the angle of deflection caused by the second refraction, right, is just that bit there. I can call that theta 1. Okay, so I'm basically splitting the angle theta up into two contributions due to the two different refractions. And so what we can say is that overall, our angle of deflection, which we're aiming to calculate, theta, is just theta 0 plus theta 1, like that. So let's think about how we can express those two angles of deflection in terms of the angles of incidence and refraction that I've defined on the diagram, alpha, beta, gamma, and delta. Now, if we think about theta 0 first, we've got a pair of vertically opposite angles. We've got this one down here, which I'm highlighting in red, and we've got this one up here. Okay, now because those two angles are vertically opposite, they're both equal to alpha, and therefore just from the geometry, you can see that beta plus theta 0 has to equal alpha. In other words, theta 0 is equal to alpha minus beta, right? So I can replace the theta 0 in our overall deflection equation with alpha minus beta. Right, now, can we do a similar thing with theta 1? Well, if we look at the second refraction that's going on at the top face, we do have a pair of vertically opposite angles because we've got that one there, which is just gamma, which is vertically opposite to that one there. But because they're vertically opposite, that's also equal to gamma, right? And therefore, in order to get this theta 1 up there, what we would need to do is take delta and subtract off this little bit, which is gamma, right? So theta 1 is going to be delta minus gamma, and I'm just going to replace that theta 1 with delta minus gamma in our equation down there. So there you go. We've expressed the overall angle of deflection in terms of our four other angles of incidence and refraction. Now I'm just going to regroup these terms here and write this as alpha plus delta minus, and then all in brackets, beta plus gamma. The reason for doing that will become clear very shortly. In fact, what we want to do is focus on a little triangle which we can make inside this diagram. So if you think about it, we've got one side of a triangle there. We could extend both of the normals like this. I'm extending them more than I need to just to kind of illustrate the point. We could extend both of the normals like this, and then we formed a triangle, right? Now, if you think about it, the angle of intersection, or the larger angle of intersection between these two normals, has to be 1/3 of a full circle, right? In other words, this angle there is 1/3 of a full circle just because of the symmetry of an equilateral triangle, right? So that angle, or equivalently, that angle there would both be 2 pi over 3 if we're working in radians, right? Because a full circle is 2 pi, and then we're saying that because of the symmetry of an equilateral triangle, that is 1/3 of a full circle, right? But we also know that the angles in a triangle add up to 180 degrees, which, if we're working in radians, is pi. And so looking at that red triangle that I've drawn there, we can say that beta plus gamma plus 2 pi over 3 has to equal pi in total, right? And then we know that beta plus gamma has to be pi over 3. So that's why I grouped the term beta plus gamma together down at the bottom left there, because that's actually just pi over 3, right? So what can we do about alpha and delta? Now, so far, you'll notice that we haven't really done any physics. This is just basically geometry. Now I'm going to actually start doing some physics, and I'm going to use Snell's law for refraction, and I'm going to apply it to the two interfaces where refraction is happening. So if the refractive index of the ice that this crystal is made of is n, and let's assume that the refractive index of the surrounding air is basically 1, which is a very good approximation, we can say that, well, 1 times sine alpha is equal to n times sine of beta, right? That's just Snell's law for refraction. And we can also write down that n times sine of gamma is equal to sine of delta, or 1 times sine of delta, because the refractive index of the air is essentially 1. Okay, so I've just applied Snell's law twice. Now, we can go back to our expression for theta, the overall deflection, and think about how we can rewrite alpha and delta. And what I'm going to do is as follows. So theta is going to be, well, if you think about this first relation, we could write alpha as the inverse sine of n sine beta, right? So it might not be obvious at this stage why we want to do that, but it is going to make this problem a bit easier to deal with, right? So let's write it like that. So the alpha is the same as inverse sine of n sine beta, right? Now the delta term in our deflection theta, we can rewrite from that second application of Snell's law, right? Delta is going to be inverse sine of n sine gamma, right? So I'm going to add on inverse sine of n sine of gamma. However, we can actually rewrite gamma in terms of beta using that relation that we derived from considering the red triangle at the top, right? Because we know beta plus gamma is pi over 3, and therefore gamma is equal to pi over 3 minus beta, right? So instead of putting a gamma there, I can put pi over 3 minus beta. And this is essentially the reason why I've chosen to express this in beta, is because that allows us to write theta, the overall deflection, as a function of just one other angle, which is beta. Right, so we've got that, and then we've got our minus pi over 3 at the end, which remember came from the beta plus gamma, which we just showed was equal to pi over 3. Okay, so this has come out looking like, well, it's not a particularly nice looking function, but it does have a certain kind of nice symmetry about it. Now, if we were to define this part, inverse sine of n sine beta, as f of beta, where f is some function, we could write theta as f of beta plus just f of pi over 3 minus beta, and then minus pi over 3, right? Because the only difference between the first and second terms is that we've replaced that beta with a pi over 3 minus beta, right? So the reason for doing this is that it's going to help us to actually visualize how theta depends on this angle beta. What we're going to do now is actually draw a plot, or at least a sketch of how this function theta depends on beta, and that's going to be key to understanding where this 22-degree halo comes from. Okay, so if I just draw a little set of axes. Okay, so there's our vertical axis, and this is going to be our beta axis. Okay, so I'm going to label that as the beta axis. I'm not going to label the vertical axis because I'm showing several different things on there. Now, we want to sketch theta as a function of beta, but first let's sketch f of beta as a function of beta, because f of beta, remember, was just this thing here, inverse sine of n sine beta. Now, the inverse sine function, basically, it's like a sine function that's been reflected in the line y equals x. Okay, so roughly speaking, that is going to have a shape that looks something like that. Okay, something like that. That is a line of f of beta, right? And it's going to stop, right? So this point here, it's just going to kind of stop when it reaches the point where the argument n sine beta is equal to 1, right? So as soon as this thing n sine beta becomes equal to 1, you can't take the inverse sine of that anymore. And so the curve just kind of stops at that point. Now, that is going to happen when beta is equal to the inverse sine of 1 over n. And so I'm just going to label that point there as inverse sine of 1 over n. Okay, so we don't actually technically need to know that in order to derive our 22-degree result that we're going to get to, but nonetheless, it's interesting to think about why the curve just kind of stops at that point. All right, so f of beta roughly kind of has that sort of shape, but f of pi over 3 minus beta, so if you know your graph transformations, you might recognize this as like a reflection in the vertical axis, because you've got a minus sign in front of that beta, but also a translation of pi over 3 units to the right. So this is a combination of two transformations of f of beta. Now, that allows us to quite easily actually sketch f of pi over 3 minus beta. So what I'm going to do, I'm going to copy and paste that, right? And I'm now going to attempt to actually flip this in the vertical axis. In other words, reflect it. So if I do that, right, we've reflected the function in the vertical axis, or technically that would put it over there. But then we would also shift it over to the right by pi over 3 units, and we would get something like this, right? So that is, this line, just to clarify, is f of pi over 3 minus beta as a function of beta. And this point up here, right, that is going to be pi over 3, because that was the amount that we shifted it to the right by. And this point over here, I guess that would be pi over 3 minus inverse sine of 1 over n. But anyway, that's not particularly important for this. Now that we've drawn both of these individual functions, f of beta and f of pi over 3 minus beta, it's fairly straightforward to see how theta depends on beta, right? Because these two functions here, because of the symmetry, right, they're just reflected versions of each other. The point where they meet, in other words, that point there, is going to have a beta value which is exactly halfway between 0 and pi over 3. In other words, it's going to be pi over 6, right? So this is like the axis of symmetry, I guess, is at beta equals pi over 6. So they're going to meet in the middle there. And so if you add these two things together, well, on the left of that point, because of the dependence of f of pi over 3 minus beta on beta, it kind of goes up as you go to smaller values of beta. Whereas if you move to the right of pi over 6, it's also going to get bigger, your theta as a function of beta, because f of beta gets bigger. In other words, what's going to happen is you get like a curve with a minimum at pi over 6. If you just think about adding together those two contributions. And we've also shifted it down by pi over 3. Okay, so that's why this point actually ends up below where the two individual functions cross each other. So anyway, what that means is this function that I've sketched as a red line is the overall deflection, theta, as a function of beta, which, remember, was not the incident angle, but it was the first angle of refraction in that prism. Now, it might seem more natural to express theta as a function of alpha, and it kind of would be, but it would be much more difficult to sketch the curve and see how it behaves without just using a computer to plot it, because theta has this nice symmetry if you express it in terms of beta. All right. So now we can actually find the minimum of that curve, right? We know it has a beta value of pi over 6, and so we could just evaluate what value of theta we get when beta is pi over 6, right? So if we set beta as pi over 6, then what's going to happen? Well, your theta, which I'm going to write as theta m for theta minimum, right, is going to be, so this first term, inverse sine of n sine beta. Well, sine of beta is sine of pi over 6. Sine of pi over 6 is exactly equal to a half, right? So this is your first term in that theta expression becomes inverse sine of, it's going to be a half, but we also multiplied it by n, right? So it's going to be inverse sine of n over 2. Now, what about f of pi over 3 minus beta? In other words, that contribution there. Well, I guess by symmetry, you can spot either just by symmetry that it's the same, right? Or you can actually just plug in beta. Pi over 3 minus beta, pi over 3 minus pi over 6 is still pi over 6. And so that second inverse sine term has the same value as the first one when beta is pi over 6. And so I can just put a 2 in front of there because we've got 2 of the same contribution. So 2 inverse sine of n over 2, and then we've got our minus pi over 3 at the end. And there's an expression for the minimum possible deflection that you can get by shining a light ray onto an equilateral triangle-shaped prism. Now, let's think about what happens if this is actually made of ice. Now, of course, the refractive index will vary slightly depending on wavelength, which is why if you look closely at one of these 22-degree halos, you'll see a bit of color separation. I think the inner edge is slightly redder if you look carefully. But to get an idea of the numbers involved, for ice, a typical value of the refractive index is about 1.31. So that's for something like green light in the middle of the spectrum. If you plug in 1.31 as a refractive index into this expression for theta minimum, you actually get theta minimum is roughly equal to 21.8 degrees, which is, well, of course, 22 degrees to two significant figures. And there we go. This is where the 22-degree angle comes from. So just at the end of the video, I want to take a moment to think about why this minimum angle actually gives you this quite impressive looking ring of light. So if you imagine you're standing at some point on the Earth and you're looking at light which has been reflected off the moon and coming straight to you, right? So that the moon is sufficiently far away that to a good approximation, we can say that the light rays coming from the moon are essentially parallel, right? So you've got a bunch of parallel rays coming from the moon like that. And what's going to happen is that the minimum amount by which one of these crystals can bend one of these light rays is 22 degrees, right? So if you look straight at the moon, right, which is kind of over there, you'll see light coming straight from the moon, right? And then you won't see anything particularly interesting going on until you look either 22 degrees to your left or 22 degrees to your right, because that's the minimum angle from which light can have been kind of bent towards you by refraction, right? And the idea is that the ice crystals in the atmosphere will, to a pretty good approximation, be randomly oriented, right? And so that means, well, if the ice crystals themselves are randomly oriented, that's equivalent to kind of sweeping over the full range of alpha values, in other words, angles of incidence, and therefore sweeping over the full range of possible beta values, right? And so that's why you suddenly see this bright ring of light at this minimum possible angle of refraction, 22 degrees.